Hey guys, my name is Sagar Batani. So I'm going to work out problem 1 on test 3 in Professor Fenton's Physics 2211 class. So the first problem states that a mysterious asteroid with a mass of 50 kilograms is traveling through space with a constant momentum of 200 in the x direction, 650 in the y direction, and 300 in the z direction, kilograms by meters per second. And so the first part of the problem asks to find the kinetic energy of the asteroid. So we know the formula for kinetic energy to be K equals momentum squared over 2 times the mass. So we're going to combine this step in terms of solving for the magnitude and squaring for the numerator of kinetic energy. So when you take the magnitude, you typically square it and then take the square root. So in this case, instead of we're just going to eliminate the square root sign because we're squaring it. So we'll have 200 squared plus 650 squared plus 300 squared to get a total of 552,500. And then we take that number, and since it's already been squared when we took the magnitude, we just have to divide it by 2 times the mass, which we know to be 50 kilograms, which is the SI unit, so we don't have to convert that. And then when we do that math, we get 5,525 joules as our kinetic energy of the asteroid. Okay, so moving on to part B of the problem, we have to calculate the rest energy of the asteroid. So we know the formula for rest energy to be E equals mc squared. So it's pretty straightforward. We just take the mass, which is 50, and the speed of light, which is 3 e to the 8th, and square it. And then we get a total of 4.5 e to the 18th joules. Alright, so part C of this problem says that suddenly a constant external force of 10, 25, 8 newtons acts on the asteroid as it moves from position 4, 3, 6 to position 1, 6, 2 kilometers. Determine the work done on the asteroid by this force. So as we know, the formula for work is force dot product change in distance. So before we can even move further, we have to take change in position. So we have to take change in position, which is the final position minus the initial position. And before we can even move on to that, we have to convert everything that's in kilometers to meters. So that's kind of all done in one step here. So we take this final position and we subtract it from our initial position, convert it into meters, and so that's what we get for our delta R. And then we have the force, which is 10, 25, 8 newtons. And we have to do the dot product on the change of position here. And so as we know, when we do the dot product, it's simply, the way Professor Fenton explained it would be, we just use the x by the x, the y by the y, and the z by the z. And when we do all that, we add it all together. And after that, we get 13,000 joules as our answer for part C. Alright, so moving on to part D of this problem, we have to calculate the new kinetic energy of the asteroid. So we know from the energy principle that the change in energy is going to be equal to the work by the surroundings. So when we expand this, we get final energy minus initial energy equals work, and then when we take into account the actual energies into play into this problem, we know that it'll be kinetic final minus kinetic initial will equal work by the surroundings. Well, we need to manipulate this formula so that we can get the new kinetic energy, which will be the final kinetic energy. And we already solved for the initial kinetic energy in part A, and we solved for the work in part C, so we just take the answer from part C, which is 13,000, and add it to the answer in part A, and that will equal the final kinetic energy of 18,525 joules. And that's how you do part D of the problem. Thanks for watching, guys. Once again, I'm Sagar Batani. And this was for Professor Fenton's Physics 2211 class.